Welcome to the talk for Demystifying mmWave V2X towards robust and efficient directional connectivity under high mobility. The emerging 5G NR V2X introduces new use cases such as vehicle platooning, extended sensors, and remote driving. These use cases help create an intelligent and safer transportation system while requiring high throughput data synchronization between vehicles and the road infrastructures. mmWave networking is a niche technology to satisfy such demanding applications due to abundant spectrum resources and high link capacity. However, the practicality of mmWave V2X has long been questioned. Due to high attenuation loss, mmWave radios have to use phased array antennas to form highly directional beams. Under a high mobility scenario such as V2X, the transmitter and the receiver may need to frequently search for the best aligned beam pair out of hundreds to thousands of candidates. The overhead for beam searching may easily become intractable. This is often considered as the most critical challenge for mmWave V2X. In addition, mmWave links are vulnerable to road blockages, including foliage, buildings, and high vehicles. Due to the sparsity of multipath, the blocked link may not be easily recovered. Finally, the directional mmWave beams open up new opportunities to achieve ultra-fine-grained spatial division multiplexing. However, the complexity of such extreme SDM may easily become unmanageable, especially under high mobility. To demystify the above challenges, we conduct a comprehensive measurement study using a mmWave V2X testbed together with a large-scale 3D retracing simulation. Our testbed consists of 4 commercial mmWave radios deployed along a 1 km road segment in a mixture of typical urban and suburban scenarios. The deployment follows the 3GPP guidelines for roadside type base stations. We customize the radios to enable codebook redesign, beam switching, multi-array operations, and real-time channel quality measurement. Furthermore, we build a high-fidelity 3D mmWave channel simulator by integrating state-of-the-art 3D environment model, vehicular traffic generator, and mmWave retracing engine. The simulation framework has been benchmarked against the real measurement in terms of accuracy, and can be reused for mmWave V2X research in general. Now we introduce our key observations and insights. Co-siting mmWave V2X base stations with LTE base stations achieves poor coverage. We observe the co-siting base stations only cover 37% of the road due to the building blockages. Of all achieved coverage, the base stations along the road contribute more than 97%. This implies the co-siting with LTE base stations does not address the coverage problem in V2X. And to achieve pervasive coverage, more roadside base stations deployments are needed. The exhaustive beam searching works well even under high mobility. In our measurement, we observe that the propagation paths are surprisingly sparse across locations and persistent over time due to the structural property of the road. As a result, a small codebook can achieve full coverage, and even the standard exhaustive beam searching takes negligible time despite high mobility. Blockage happens infrequently in mmWave V2X and can be effectively mitigated through simple solutions. We observe a 3.83% overall blockage rate, mainly due to buildings and tall vehicles. The non-live-side paths are mostly distributed around line-of-sight paths, hence the blocked link can be quickly recovered by steering its beams towards the non-live-side paths. For links with no non-live-side paths, blockage probability can be significantly reduced by raising base station height or leveraging the 3GPP-NR multi-connectivity feature. The spatial multiplexing schemes in mmWave V2X can be simplified due to the high directionality. The inter-cell interference can be significantly reduced by using RX beamforming on the UE side. 3GPP introduces a sophisticated hybrid beamforming scheme to serve multiple UEs simultaneously without interference. However, we found that a simple spatial multiplexing approach can achieve superior performance than hybrid beamforming, thanks to the spatial orthogonality. In summary, we presented a real-world measurement and a large-scale 3D retracing-based characterization of mmWave V2X networks Please refer to our paper for more insights and details. Thanks for watching.